Wonderful. Hello, everyone. How's it going? We have a new episode tonight of Vibe Space with a very special guest, Axel Kloth from Abacus Semiconductors. Axel has been doing semiconductors for 4 decades now, 4 years round. And today we're going to learn all about AI and bottleneck of inference and Axel's takes on semiconductors, what he's building with Abacus. So stay until the end, get your questions ready for Axel, and we're going to have a great conversation tonight. Welcome, Axel.
Wonderful. Thank you very much. Thanks for having me, and thanks for the nice intro. So yes, I've been doing this for a little while, but yeah, let's go back a little bit in history. So I'm a physicist and computer scientist by training, and I've been involved in all kinds of stuff that has to do with semiconductors and has to do with the use of semiconductors, even semiconductors in high-performance compute and supercomputers like the Cray YMP that many people may know because it looks like a very beautiful piece of furniture with a seating arrangement, but was a little bit more expensive than that. Ever since then, I've been involved in semiconductors and building stuff for computers, for supercomputers particularly, based on modern architectures for semiconductors, and that ties directly into the AI field because you may have heard of this little thing called AI and ChatGPT. It's beautiful, it's wonderful if you know how to use it properly, but it also uses a lot of energy and a lot of compute cycles, and I'll come back to why and how and what the reason for all of that is. I've worked in Germany for about 10 years at Siemens, and then Siemens decided that it would be better if I came to the US because all the crazies go to Silicon Valley to invent new things. And so they said, hey, go do something new. Don't bring us anything that we already know. Just do the new things, which I did. And then after 2 years, I still and nevertheless got bored of it and then quit and started a vision processor company. And after that, we invented a lot of things that I just found the patent plaques today. They were the first use of AI in vision processing because ultimately these things are all tied together. And that was in 2004 and 2005. And then sometimes the perils of being too early are that VCs don't quite understand what it is that you're doing. And me and my co-founder were being told that everybody wants to drive their own car and there's no need for anything that would be called advanced driver assistance systems, and that we were stupid and better go home. So after 9 years of trying, we gave up and said, okay, fine, we can't get that funded. I started another company, this time focused on high performance compute. And while I was working on solving some of the problems inherent in high performance compute, I was pulled into something that required a new type of a processor, but for security, not for high performance compute. I did that and then spun that off into a new company. That company got funded. I raised $22 million for it. By now, the company has raised another about $160 million. And that company finally has, I think, product out and is selling to customers. I, of course, again, got bored of all of that and left after I wrote all of the initial patents and started the company down the path for the development of the chip and started this company, which is Abacus Semi. And I named it, of course, after the ancient device, the first mechanical device to aid people in doing simple math and computation. Now, this again ties directly into AI. And as you may have noticed, AI is in everybody's mouth. Everybody's using AI. Everybody's talking about AI. Everybody is complaining about AI because it from time to time gets you wrong output. It gets you hallucinations, gets you all kinds of stuff that may or may not be desired, but it's sort of understandable from a standpoint of the math under it and the compute behind it. And so that's why I started this company, because the amount of compute needed to create a foundational model, such as the one that underlies ChatGPT or any of the competitors, that's of course something that requires, first of all, enormous amount of input data, but at the same time also enormous amount of compute to create the model, and then use that model to infer the answers to the questions that people pose to ChatGPT and Anthropic's Claude and all these others, right? So that's what I did, and that's what the company is focused on, and that's why we believe that AI is going to be something that parallels, if not eclipses, the importance of the web. And I have a hunch that a lot of the listeners here may have been born after the web came into existence. So, initially we had computers, but they were not networked. And if they are not networked, then everybody is on her or his own, and that's about it. But once we started networking computers, the computer became the net, and the net became the computer. And the benefit of that is that all of a sudden you can now address much larger scale problems, except for when you have things that are, like called nearest neighbor problems, finite element methods. Then you need to have a lot of compute, and you have to have a interconnect that connects processors and the accelerators that effectively work on the workloads, connect them in a fashion that has very high bandwidth and very low latency. And latency oftentimes is more determinant of the performance of the system than bandwidth. And the simple explanation that I always use as an analogy is, when I talk to somebody, and that can be you all, then you have the ability to immediately ask a question. In these modern times with tools like chat, like any kind of a many-to-many. Exactly.
Yeah.
Right. So the benefit is you can immediately ask me a question, and the effective bandwidth is very high because you can ask and I can immediately come back with an answer. Now imagine you do the same thing, but except for, the difference would be you don't do it over a real-time medium, you do it over sending a letter through the New York post office, right? In that time that it takes to get from you to me and back to you, the effective bandwidth of the communication has decreased by orders of magnitude. And that means that it's much harder to work on a shared problem in a reasonable time frame if the latency between any two participants of anything, communication, math, whatever it is so high that the latency determines the effective bandwidth and not the peak bandwidth between any two members of that group. Right. So I don't want to get too theoretical, but you're all welcome to ask questions in the chat. And if there's anything that you want me to explain about AI, how it works, and why there is a new generation of chips needed to solve the AI problem, both in the crunching of the data to create the foundational model, and then later on in the inference part, where in fact one new member of a group can ask a question. That question will be answered by the model and some additional software that extracts the gist of the question and then poses that to the model and creates the answer, right?
Yeah, suddenly this topic of hardware becomes more and more popular. Even if people don't know about the limitations, it gains popularity because of the usage, the software on the other side. By the way, Axel, your explanation on the latency and the bandwidth is great. You could
Well, thank you.
break it down to simple terms, right? Well,
Exactly. I try to explain things in a way that most people understand. And so, if it's still over your heads, let me know, and no problem with that. I'll try to figure out how to explain it in a different way. But, one other explanation I wanted to give is that for the past 20 years, computers, for the most part, have relied on CPUs to remain flexible, but the workloads are executed on usually what is called an accelerator. And those accelerators today are GPGPUs, general purpose graphics processing units. And they are used because they are massively parallel. You get lots and lots of compute cores in a single GPU. And that's a benefit because you can parallelize the problem of creating the model easily. And by doing that, you can now make the creation of the model much, much faster than you would be able to do that with software. And the analogy for people I use that are not deep into computer science is always, if you think about an orchestra, The conductor isn't playing any music, but the conductor keeps everything flexible. The music is being played by the musicians with their instruments. And if you take that as an analogy, then you immediately understand why it's important to have lots of different musicians and instruments, meaning different types of accelerators, to execute the workloads. But at the same time, you still need a CPU because the conductor chooses which piece of music to play, when to play, how to play it, at which speed, and whether it has to be transposed for different instruments or not. Right? So the flexibility comes from the CPU, and the performance comes from the accelerators. And that is the basic and fundamental thing that has changed in computer science over the past 20 years. And if you followed computer science for a while, you may have noticed there were wars about RISC versus CISC. Those are all over. Those wars are gone because that distinction is not relevant anymore these days. Then there were wars about the instruction set architecture, x86 versus ARM, today RISC-V, right? And then in the earlier days, there was the DEC Alpha and MIPS, and there were plenty of different instruction set architectures for processors. But today it's all consolidated into x86, which is Intel and AMD. Then there's ARM with its architecture and multiple architectures, in fact. And then there's a new one coming up for past 10 years that has gathered a little bit of a following, and we use that core too. That's called RISC-V. It's the 5th generation of RISC processors. And I think so far it has the fewest drawbacks of any of the RISC processors out there. But that's what we're using to stay flexible. That's not what executes the workloads, but that's what keeps us flexible so that we can work on any workload that's needed with any data size and any data format that's required to solve that problem optimally.
No, that's great. I remember when the PC master race started and people were buying better and better GPUs for playing games with better resolution, more polymers and all, right? This is interesting to see how it's surfacing again because of now the use of GPUs to process inference for AI, right? And I follow the talks that general purposes GPUs are not optimal. There are a lot of research on natural language processing units like Grok with a Q that was recently bought by NVIDIA, these kind of hardwares, right? Mm-hmm. So actually, since you're so good in explaining complex things with simple terms, how would you explain for a normal AI user that mostly uses AI over the web, over servers like ChatGPT or cloud, or maybe some of them are running locally with Llama or with Llama C++, something like that. How you would explain this bottleneck? And maybe you want to introduce the proposal for Abacus that I found super interesting. And if you can break this down in simple terms, that's going to be worth gold here in the channel.
Yeah, sure. So the simple matter of the fact is that any of the big providers of foundational models have scoured the entire internet, and they have taken the data. They have written what is called a bot. The bot has scraped data from everything and everywhere, every website, every book ever published, literally everything, even movies. And that data is taken as input to create what is called a foundational model. And the idea behind that is if you only have enough data and you have enough compute to create a foundational model, to crunch the data into a model, then you can infer anything you want with a simple request to the model and the inference engine so that you get the answer that's desired. And that can be on text, that can be on pictures, it can be on movies, it can be on anything that is video, streaming or not. And the idea behind that is that once we do that and we take all the data that's there, this intelligence becomes more intelligent than a human being and becomes basically a super intelligent entity all by itself. And that would then be called artificial general intelligence. And everybody who's on the market today tries to do that. And first of all, it takes a lot of compute. Second, it takes a lot of compute, not only during the creation of the model, but the more users are using it, the more inference needs to be applied, meaning the more requests go to the model and then come back as an answer. And that is also very computationally intensive. But that can be done at the edge, and it can even be done in a user's computer, which is why processors that have a built-in inference accelerator will be faster than those that have to do it in software. Right? If you have it at the edge, then even your cell phone could use it. It doesn't need an accelerator for the inference. And if you do it directly at the smart carrier edge, you can push it out even further, which is advantageous for the individual user, because the individual user doesn't have to have a device that has a hardware accelerator for inference. But it gets more and more concentrated in the power consumption at either the edge or the smart carrier edge or wherever you want to put the demarcation line. And so that's a little bit of a problem, because now every data center will have to be updated to a level of power consumption and a level of cooling that was unthinkable even 10 years ago. So, 10, 15 years ago, a server rack was considered very hot if it consumed anywhere between 15 and 30 kilowatts. Then we went to 78 kilowatts. Now we're at 130, and we're planning to go to 200 kilowatts per rack. So 5 racks today would be a megawatt. That used to be a very large-scale data center in terms of power consumption, right? So first of all, you now have to get a megawatt to the data center. And second, well, guess what happens with a megawatt being consumed? It creates heat. So now you have to get rid of a megawatt worth of heat, right? And so data centers today look very, very different from data centers from 10, 15 years ago. You usually don't see the racks stacked next to each other, because between racks, you now have to have a chiller. And the chiller can either be air or it can be water. And in all modern data centers, it has to be water, because you can't get rid of 200 kilowatts in a rack with air. Air cooling just isn't good enough for that anymore. 130 kilowatts basically is already exceeding what's doable with air. So all of those, they have to either be spaced out very, very wide, or they have to have water cooling. So a data center today that doesn't support water cooling is pretty much already outdated. And that's something that the industry hadn't seen before. It was very, very few computers that were in need of water cooling. Today, it's basically a prerequisite. If the data center doesn't support water cooling, then you can't deploy the newest hardware that relies on the fact that you can water cool those devices. And, things change, and that's just the way it is.
Well, that's crazy. And this has to do only with like usage of chatbots like GPT and all, or is it about the new wave of image and video? Because these are way, way more consuming, right?
Correct. So right now, most of the public providers of foundational models, they have gone through everything that there is: text, pictures, video, movies, all of that. But the ability to create good answers is better on the text-based models than it is on the pictures and the video models. Because the problem with AI today is the understanding of a scene in a picture or in a video is still lacking and takes even more compute than the understanding of a text. If you feed a text into an AI foundational model creation tool, it will be able to create that foundational model with a relatively moderate amount of energy needed. However, a picture is different, and a video is even more complex, because the understanding of a scene or of the contents of the video is in need of even more compute, because first, the AI intelligence and the instance will have to understand what the objects are in that particular picture or in the frame, in a field of vision, or in a part of a movie. And that, of course, takes a lot more energy to understand that, because you have to identify the objects, you have to identify what they are doing, the kinematics, everything related to that. And then you can draw conclusions as to what the meaning of these entities are in that either frame or in the picture. And that's, of course, even more computationally intensive. And so therefore, AI and AGI, that is just predicated on text, that's already enormously computationally intensive. If we now look at pictures and videos and entire movies, that's yet another level of abstraction, because usually movies have an underlying idea, an intent. They have a train of thought through it. And humans understand that, because once you see a movie and you watch it, you can say, oh yeah, this was about good people versus bad people, or these versus that. Humans are relatively good at extracting this kind of information. That cannot be done algorithmically. So that's something that now requires a lot more compute, because it's not algorithmically done. It
Yeah,
again
I
needs
see.
to be inferred.
I see the perfect storm coming. Axel, if you allow me, I would like to pick your brain on your 4 decades of experience and ask what is going to be of the future then. I just saw this week the announcement of the C Dance 2 from ByteDance. It's a video generation model. All of those voice models, 11 Labs just created a new one that doesn't sound like a computer at all. I've seen the RAM prices, memory prices skyrocketing. What's going to be for the next year or for the next month? Do you see a huge collapse of the hardware inference industry? Do you see the current GPUs being able to handle that? Or how do you see the market evolving?
Well, I think throughout human history, if there's one thing we can all agree upon, is we never go back on our demands. So whatever we demand today is less than what we will demand tomorrow, right? So I do not anticipate that we will ever go back to a level of, just a Google search is good enough. That's just not happening. I think the demand for compute and for intelligence and for, human and artificial intelligence will just rise. That amount will go up. There's no going back, right? The question is, how do we fulfill the demand? And that's, of course, where new architectures for chips will have to come into play, because GPUs cannot continue doing this, because simply we can't afford the level of energy consumption, right? It's not feasible. You can't put a nuclear power plant next to each data center we build for AI. That is not a
Oh,
feasible answer to the problem, right?
that would be so cool. Just kidding.
It's not feasible. I mean, in the US, it takes 15 years to get the permit for a nuclear power plant and 30 years to build it, right? So if we start today, 45 years from now, we can start building data centers that use that energy. And that's not feasible. So what
Yeah.
we have to do is we have to figure out a way to make better use of the compute that can be offered. And I think that is where we come in, because we basically say, the performance of an individual chip is important, but the performance of the system is more important. And if you look at system performance, then the chip performance takes second fiddle to the interconnect, which is the example I brought up before, the latency, right? So if the latency can be reduced between any of the processor cores or the accelerator cores that are in use to create the model and to infer from the model, then the system performance, the real life performance available to the user, will be greater with a system that takes the interconnect to the next level versus takes the performance of a single chip to the next level. Because again, the performance of the single chip today, where can we go? As semiconductor professionals, we know Moore's law has flattened out, right? So Moore's law, we don't have twice the number of transistors every 18 months anymore. That's not happening, right? We still have a moderate growth of the number of transistors we can put on a die, but that's going to be limited and because of lithography, that's going to be limited very simply because we can't get rid of the heat, right? That's one limitation. The other one is we can crank up the clock frequency, but again, that creates more heat, which in turn we can't get rid of. And so therefore, we will still have a growth of computational performance per chip, but we need to be able to make them communicate seamlessly with each other and with the CPU and with the memory in case any of these processor cores or accelerator cores have to share data. And so the paramount problem we need to fix is the communication, particularly the latency, and the access to shared memory in a way that makes it feasible. Because I may have to dive a little bit more into tech again, but processors today are fast. Memory is dense, but not fast. So what happens is all processors have something that's called a cache, right? A cache is an interim storage that is faster than the external memory, but not quite as fast as the memory and the registers inside the processor. And that's done so that we can hide the latency, again, the word, right? Favorite word here, of memory. Because memory, again, is nice and dense and all fine and dandy, but it's not fast. So if a processor executes code, then the prefetch unit will say, hey, I can predict what you're going to need to fetch next. So the prefetcher will get data from DRAM, from the main memory, and put it into the cache. And the cache now has it available to the processor at lower latency because it fetched a whole lot more data. Because again, memory external is dense and it has reasonably good bandwidth, but terrible latency. The cache has very high bandwidth, low latency. So the cache prefetches instructions so that the processor has it available. Okay? You do the same with data, but of course, data doesn't have the nice locality. You can never predict where the next data that you need is going to be stored. It can be where you think it is, and if you're unlucky, it's not, right? So then you have to wait. And the problem is, once you wait, you waste energy, because when you wait, you can't put it to sleep. You don't have enough time to put something to sleep and wake it up when the data is there. But you don't produce a result. And because you don't produce a result and you keep burning energy, you're not efficient, you're not effective, right? That's the problem we need to solve. And we do that, and particularly when you come to memory. And if you think about if N processors have stored the same data that they fetched and prefetched from memory, and these 10 processors now work on something, they must know that, look, another processor has the same data that's mirrored in their cache. Maybe it has expired. It's not valid anymore because the other processor has already created the result, right? So that's called cache coherency and memory coherency. And the problem is the more units you have working on a single thing, and the bigger the problem is, meaning you need more memory and more caches, the more traffic you have between processors saying, hey, this is not valid anymore. Don't work on it. Throw it out. Fetch new one, right? So that is called metadata traffic. It's not really the net user data. It is traffic that is created just to signal the validity of data that others may already have in their cache. And that needs to be solved if we want to make sure we can outsource problems to accelerators and that they all can combine to be working on a single problem in a very large scale memory. And so that requires smart memory. And that's what we have developed as well.
Oh, that's interesting. And one of our watchers today even asked exactly about this, about the techniques that you had there in 2004.
Yes.
And they are finally surfacing today. So what's likely to see? I guess it happened as well with your vision company that did the car stuff. Now Tesla is doing that.
Yes.
And now the memory the metadata caching. So how do you see that? It's interesting to see that the industry is finally catching up on those trends, right?
Well, it's strange, and in a lot of ways it's frustrating because, if you're too far ahead of everybody else and you can't pull everybody with you, then you will not raise any money. And that's exactly what happened to Perimex, my prior
Yeah,
company. And that is frustrating to see because we knew, me and my co-founder, we knew it was needed. We had the solution. The solution solved the problem, right? Except for we could not convey that message to investors in a way that they said, "Oh yeah, we understand. Here's money. Go make it work." Right?
yeah,
Could not convey that message, and that was very frustrating.
I imagine. Do you have any ideas right now that people are not understanding? Maybe this would be a safe bet, right?
Yeah, plenty of them.
No, that's great, and this is also inspiration for a lot of founders out there. If you have a very good idea, maybe it's just about timing, about maybe you're too early or maybe late on an
Yep.
idea. So that's interesting. Now coming back to the discussion. So when we speak about LLMs, the training or inference, are you able to speed up the training process or reduce the latency or the workload on the inference by using the metadata, the caching and parallelization that you mentioned?
Yeah. So the smarter you make the caching, and the smarter you make the distinction in between, what is it called, a coherency domain, and what is not inside the coherency domain, the more intelligently you can make that distinction, the better the performance of the system will be, right? Because again, memory is faster than disks and SSDs, no doubt about that. But a processor, it's much, much faster than the memory. So the more you can make use of the cache, and the more you keep that in a state in which the rate at which you hit it, called the hit rate, the rate at which, in fact, the data that you need from memory is already in cache. So the better that hit rate is, and the better the interconnect between processors and accelerators and the smart memory in general is, the better the system performance will be, right? And if your hit rate suffers because the data is not cooperating, then the algorithm for getting the data from memory to cache should be adjustable. And so we use an AI instance to predict where the data is going to be. So our caching is, in fact, uh, it's adjustable. It's based on AI. So we use AI to optimize AI.
Like a neural network or machine
Yes.
learning model that you run?
Yes.
How does that work, if you can tell?
Yeah, it's effectively a neural net that allows us to predict where the accesses are coming from and where they have to go.
Oh, that's very interesting. One of our guests watchers asked exactly about that. If we can use code to help on the computation, his question is more like, can we improve the software inside of the hardware? So what you're saying is that using some sort of software inside the processing of the hardware can improve the whole processing?
So theoretically possible, but the issue you're going to face is that executing instructions is always going to be orders of magnitude slower than putting that in hardware. So if you put something in hardware, like an adaptive caching algorithm, then it
Mhm.
works at the speed of the CPU, at the CPU clock. If you do that in software, then first of all, you now have to fetch additional software to predict where the cache hit would be, and then feed that info into the cache so the cache can prefetch, right? So certain things can be done in software just fine. Others will suffer greatly if you try to put them in software instead of making relatively simple hardware.
I see what you're saying. It's not something that we could put in like an ASIC or something like that. It needs to be done in the CPU dynamically, right?
Well, I mean, ASIC just means application specific integrated circuit, right? So in
Yeah,
our case, the processor is a processor, but in essence, even a processor is an ASIC. And our accelerators are all ASICs, but they have processor cores in them to do certain things, right?
I see what you're saying.
So the distinction between just a fixed function ASIC and the processor, that's long gone, right? This most ASICs these days contain processor cores to keep them uh, flexible, so you can adjust the deployment. And a lot of processors have a lot of hardware finite state machines in them to execute functions that are being used over and over and over again, right? So the distinction between fixed function and programmable is, I wouldn't say, is not useless, but that has softened that.
I see. Well, I know nothing about LPUs or GPUs, that for LLMs. It's just that your proposal of using neural net, you said, right, inside the inside the logic itself for processing the AI, like kind of inception, like seems like a breakthrough. I would see that becoming a big thing easily.
Adaptive caching has been around for a while, but it's for the most part it looks into the past and into a very distant past. And the faster you can make your adaptive caching algorithm, the better you can adjust to the changing requirements of data fetch and write back, right? And so therefore, what we have is certainly different from what has been around for a while, but the idea of an adaptive caching algorithm has been around for at least the last 15 years.
Interesting. But have you seen someone using that for AI inference so far or training?
I don't think anybody other than us does that.
That's super cool. Well, we're getting some alpha here. Axel, do we have time for more questions? We have a
Sure,
couple of them here in the channel.
sure,
Uh,
absolutely.
Gina is asking, what's the biggest challenge right now in terms of adoption? Do you need to work with chip manufacturers directly, or is it hardware manufacturers? Yes, speaking about Abacus, right?
Yeah. Yeah. So the biggest challenge for us is to raise funds because ultimately I've self-funded the company. I've seeded the company 5 years ago, and 5 years in Silicon Valley without income is a long time. So we at some point in time need funding from the outside because I want to be able to retain my team, right? Because ultimately, no matter if you've ever been in Silicon Valley, you need a team. You can't do things by yourself, right? So that's the biggest challenge. That's the fundraise. The adoption, everybody we've talked to so understands the tech, understands the benefits we bring, and understands that this is a change in status quo. This is not just an evolutionary step. This is a step ahead that the competitors can't really deal with, and they can't negate the advantage we have because of the interconnectivity, right? Uh, we do work with chip manufacturing, but we design the chips ourselves. So this is our core competency, right? We design the chips. We create all the way from the model, the simulation, all the way to the blueprint. That's what we do, and then we give that to a manufacturing company, and they make the chips, and then these chips will go into servers. Probably not Dell or Supermicro. They are pretty much married to Intel and AMD, but they will go to the other server manufacturers, and pretty much all of them are in Taiwan these days. There's not a single manufacturer of servers left in the US or in Europe, right? So they're all pretty much in Taiwan. I think a few maybe, I think there are quite a few in Malaysia now and in Singapore. So that's all in Asia, right? And the hardware manufacturers, they will then, of course, sell those servers to the operators of data centers that are focused and pretty much exclusively focused on AI, because the general purpose stuff, we probably wouldn't provide a vast efficiency upgrade over existing stuff if you just have a look at a normal server that is there for file services or for getting data from disk to another disk or shifting from disk to the network. We might still have some efficiency gains on top of what's out there today, but that's very likely by itself not good enough to go against an established vendor, right? So only if the mandate is to use that for AI, then we have an advantage that the others can't compete with.
Yeah. Also, could you use this opportunity to explain a bit more about the hardware industry that we barely don't hear about? Abacus is fabulous, right? So
Correct.
how the supply, maybe in 2 minutes, explain how the supply chain works and how you position, because most people know like NVIDIA and the big stuff, but they don't know about the whole industry that is around it.
Yeah. So for all of those that are not familiar with how the semiconductor industry works, totally understandable because it works differently from any other industry. Imagine Mercedes, they design their cars and they build their cars. Nissan designs their cars, builds their cars. If this were the semiconductor industry, then Mercedes would design cars, Nissan would design cars, and some other entity would build the cars to the specification of Mercedes and Nissan. That's exactly how semis work. We're called a fabless semiconductor company because we design, we engineer, we model, we simulate, we create the blueprint, but we don't build a single CPU or accelerator. That's done by a contract manufacturer. And we use the same contract manufacturer that NVIDIA uses and AMD, right? So that's a very big difference between the semiconductor industry and the industry that pretty much determines everything else, right? And the reason for that is a fab today costs between 25 and 30 billion dollars, not million, billion. The most expensive automotive fabrication sites, I think, were BMW's Spartanburg facility, and that was less than $5 billion, right? Most of them are much, much smaller and cheaper than that. Even the Tesla fab, it's, I don't know, was a billion or billion and a half, right? So that's nothing compared to what the expenses are in semiconductors. And the reason for that is that semiconductors thrive on volume, right? If you have a look at what the development of a CPU or accelerator costs, and if you have a look at the number of transistors on a die and how many of those you would have to produce to make a profit, then you would see that all that counts as volume, right? So let's say a company spends $100 million to develop a processor. Making that processor through the contract manufacturer may cost $1,000. Who cares, right? So if you only sell one of those processors, you would have to charge $100 million plus $1,000 for it, right? If you sell 100 million of them, then the manufacturing cost will still be $1,000, but your fully prorated cost of the development will be $1 per processor. So you can sell that for $2,000 and you still make $999 of profit, right?
It's
So
huge
that's the big
problem.
difference, right?
Yeah.
And then the other thing that most people don't quite understand, a car today consists of about 5,000 parts, not more than that, not vastly more than that. It's anywhere 4,000 to 8,000 parts. If you buy a processor, a modern processor today, you will see that there's anywhere between 20 billion and 100 billion transistors on it, right?
That's crazy. Yeah. Crazy
So
numbers.
if those were parts in a car, you can imagine what a car would have to cost, right? And
Yeah.
cars are not proportionally more expensive than that, right?
Yeah.
So the semiconductor industry has flourished just because of the fact that you have fabulous companies that design something, engineer something, make the blueprint, and then one company that makes the semiconductors for pretty much all of them. There are very few of those contract manufacturers out there. One is Global Foundries, the biggest one is TSMC, then there are a few specialty manufacturers. The memory guys still all have their own fab, so Micron has their own fab, SK Hynix and Samsung, they all have their own fab, a bunch of Chinese companies. But for the most part, specialty is still owned by the developer because they are specialty. But if it's bulk CMOS, Apple, AMD, NVIDIA, they all use TSMC, right? And
Interesting.
and that's why the cost is so low. Because imagine if 5,000 parts in a car might cost you $50,000, which is the average selling price of a car today, right? Think about what 100 billion transistors on a chip would cost you if a single transistor costed the same equivalent, right? Would be
Yeah,
unaffordable, right? Simply
yeah.
unaffordable.
That's interesting. I guess we need to get some more alien manufacturing units for us to. Just kidding. This is a crazy theory out there. We do have a lot of very good questions. Let me pull some of them here.
Yeah, sure.
Thor Hegeman, sorry if I misspelled your name, is asking about if you can test something about Abacus, for example, in a Torch pipeline or
Yes.
something through API,
Mhm.
because sometimes it's a good way to drive adoption, right?
Yes, correct. So I'm glad you asked this because that's something I alluded to, but may not have been entirely clear before. All of the workloads are executed on accelerators today. And if you look at Torch, well, it's PyTorch, right? It's a library called from Python. And so for as long as the manufacturer of the accelerator provides you with a plug-in or an API or the framework that allows PyTorch to access that particular accelerator, you don't need to worry about instruction sets because Python is interpreted anyway. And anything on top of that is going to be interpreted. Anything below that is not something that is visible to the instruction set. That's just handed over from the CPU directly to the accelerator using that framework. So yes, the APIs, they separate the high-level stuff from the low-level stuff, and therefore the high-level language, including interpreted and even compiled languages, from all of the frameworks of the API that are under the processor, and then will do something that initiates a workload execution on the accelerator. So yes, therefore, the accelerator manufacturer will have to provide the framework such that all of the usual culprits, CUDA, OpenCL, OpenACC, Torch, PyTorch, of course, TensorFlow, that they can be executed without the user noticing that there is a different hardware under it, right? The idea always was, and the trick and the entire predicate is that, again, if you use hardware to execute your workloads, then that has to be done through APIs, because if we had none of that, it would be impossible for the average, even for a very good programmer, to create that framework because they don't know how our processors and accelerators work, right? So yes, the framework will have to come with the accelerator.
Interesting. For anyone out there looking to try it, do you have any recommendations for TensorFlow, JAX, or PyTorch or Keter, something to use Abacus right now?
So we are not making recommendations what the user should use because that's a highly subjective decision, and we don't want to restrict the user in what they are using as a high-level language. So we provide the frameworks for everything that is today in use, and then the user can make the decision which one of the frameworks to include and to use.
Okay, that's good. Well, we do have more questions. Tor also asking about if it's just for the servers because of the form factor, or if it could be used in desktop units as well.
Yeah, so theoretically, yes, of course, you can put anything that goes into a server into a desktop, right? But the problem is most people think of desktops as relatively low performance, relatively low cost, x86, and for the most part, Windows, and limited ability to provide power and very limited ability to cool, right? So theoretically, yes. In reality, you won't put a $35,000 NVIDIA GPU into a desktop anyway either, right? So with us, it's going to be the same. It's going to be a limit on power. It's going to be a limit on the cooling ability. And in a single desktop, you would put usually only one of those accelerators in, and that would negate our ability to interconnect many of them together, right? So if it's one versus one, then we don't have a performance advantage or power advantage over NVIDIA. If it's 100, then yes, that's a very big difference.
Yeah. The more you have, the more latency you eliminate, right?
Correct.
That's good. The next two questions are quite related. One is not a question, it's like, Gina, thank you for the answer. Point about the go-to-market about the manufacturers in Asia.
To some degree,
And
yes, because ultimately we know all of the server manufacturers, but of course, we would have to convince the end customers to buy servers based on our stuff versus servers based on AMD, Intel, and NVIDIA, right? So in a lot of ways, yes, we have to go to market through the server manufacturers, but we at the same time also have to educate the end users because the server manufacturers are not the end users.
yeah, yeah. And the next question is quite related from Augusto as well, asking about when you're raising capital, if there is anything in your pitch, because it sounds like a revolutionary idea. It's not just an incremental change, it's a new paradigm. Now, how you can position that so that investors can know that this is the real deal or not just following a trend.
Well, investors usually are pretty good at figuring out if they have the tech chops to assess the technology, right? So usually VCs have technology evaluators that would look into what we are doing and every else startups are doing, right? And so one thing people usually look at is history. And we, of course, have a history of being involved in AI, and that's provable, right? So the patents out there, they prove we've done it 20 years ago, right? The patent that we have now proves that what we do is in fact novel, is in fact a foundational change. And that's the first indication. The second, of course, is that if you want to solve an artificial intelligence problem, a challenge, most users and most VCs are smart enough to say, okay, how do you do and how do you deal with very large memory? How do you deal with sharing the data across many, many units? And if you don't have a consistent and plausible answer to those, then VCs very quickly smell that there is something not quite right, right? Does it prevent VCs from making a mistake from time to time? No, we know of quite a few instances in which the VCs have been fooled by companies that didn't have what they claimed they have. But in our case, we always play open kimono. So in other words, if somebody comes and says, hey, we want to see what you have, be my guest. Look at everything you want. Knock yourself out.
Yeah, yeah. That's said that sometimes the investors they buy the hype instead of actually doing the due diligence, right? But
Sometimes that
it,
happens, I agree. And to some degree, there is a herd mentality. If one of them does one thing, all of the others follow, right? I mean, that's
yeah, yeah,
certainly true. But as I said, for the most part, VCs either say we can't judge it because we don't have experts, or they will find experts that can make a recommendation.
yeah, yeah. That's the good part, right? Let me pick a handful, or actually a couple more of questions so that we have time.
Sure.
Thor was asking when you say about the manufacturing in Asia, he was
Yes.
asking about the TSMC in the Phoenix location, and
Yes.
he also asked about the CHIPS Act for boosting domestic production, and now asking about what you see in the horizon.
Yeah.
So
So let me
those
go to
comments.
the TSMC Phoenix first. So TSMC Phoenix is set up for a 5 nanometer process, and that's something we can't do for very simple reasons of economics. On top of that, all multi-project wafers, so prototypes, they're all made in Taiwan. So Phoenix doesn't make any multi-project wafers, and so therefore our prototype is going to be 12 nanometer FinFET at TSMC, and that by definition is in Taiwan. If we go volume production, then yes, that could theoretically be done in Phoenix. By the time we're done, they would very likely be down to like 5, 3, and 2 nanometers. That would be feasible. We could do that, no doubt about that. But prototypes are always done in Taiwan. Every single prototype that TSMC makes on any progress and any process node is in Taiwan. So volume production in Phoenix is at some point in time possible. Prototype, no.
And what about the chip? Yeah.
The CHIPS Act, yeah. So the CHIPS Act was a good idea, and a company was specifically started called Netcast by the Biden administration. Got to get out of the sun here a little bit.
It is sunny out there, right?
Yeah,
California
there was no sun whatsoever yesterday, so today it's more than needed. Anyway, so the Biden administration had set aside $270 billion in the CHIPS and Science Act. The CHIPS Act money, $54 billion, was allocated to an entity called Netcast. Netcast was a VC that was intended to be a limited partner to other VCs. And that was done on purpose because the Biden administration acknowledged that they didn't have the technology advisory board that could tell them where to invest and where not. So they created a VC, Netcast, that was intended to distribute money as a limited partner to VCs that are in the semiconductor business and were able and are able to determine in which companies to invest. So the chain would have been government money to Netcast investing into SLPs, into VCs that invest in semiconductor companies. And that idea was, in fact, a good idea because, again, I don't think that a government should be in the business of being in the business, particularly not semiconductors, right? And so the idea was good, but of course, Trump killed Netcast. That was dissolved. And therefore, the money is allocated but hasn't been spent. There's a lot of money out of that CHIPS Act money that went to Intel and that went to Micron, and a very limited amount of money went to TSMC and Samsung for their fab operations in the US.
Interesting. Do you see that, just add on to the question, do you see that changing soon or under the Trump administration? Or?
Let me put it this way. I can't find a single piece of evidence that the Trump administration acts on scientific data or integrity. Therefore, I don't think they're going to return to something that makes sense.
Okay. Well, but that's a short sentence, but loaded. You have a very strong opinion on that, it seems, Axel. Well, we were about to end our stream as well. I would like to thank everyone that's watching today. Thank you a lot, Axel, for coming and sharing all of this knowledge, explaining so well. Do you have any call to actions or directions if you want to reach out to you, know more about Abacus and try it out?
Yeah, you can go to our website. It's abacus-semi.com. And if you want to contact me, that's fine. It's axel.kloth@abacus-semi.com. Contact me anytime. If you've got any questions, I'd be more than happy to answer them. If you have any suggestions, that's fine too. If you've got money burning a hole in your pocket and you want to invest it in us, I'd be more than happy to talk to you as well.
That's wonderful. Yeah, any hardware VCs watching this video to come to our channel, to one of our partners in distribution, could be a great idea to connect with Axel. Not a financial investment, of course, but I'm personally convinced that if this guy predicted all of that 10, 20 years ago, he know what he's doing, right? I can vouch for you, Axel.
Great. Very good.
Thank you very much for coming tonight. Thank you all for watching. This is going to be our YouTube channel, and you can follow our calendar for all of these events on Luma. We put this here, so you can go to luma.com/ventureminer, subscribe to our calendar, and you're going to see all of this content there.
Wonderful.
Amazing.
Thanks for having me.
Thank you very much, Axel. I'm going to
Thanks.
wrap up here. Thank
Okay.
you all.
Thanks.
Bye.
Bye-bye.